Yes, got it. All right, thank you for inviting me to the talk, and thank you all for coming. The work that I'm about to present to you is work that I've done in collaboration with folks at Google Brain, including Alex Damore, who is one of the panelists. All right, here we go. I'm going to quickly give you an overview of the whole talk so that you can place this work in sort of a sea of related work. The narrative that we've seen in the last few years has been that we can build these super accurate models and specifically deep learning, deep neural networks that are great at making these predictions. But what we've seen is that they're increasingly reliant on shortcuts. And for now, we'll say that shortcuts are spurious correlations that exist in the data. And when these spurious correlations break, the model is no longer able to give these like stellar accuracies that we see at training time. So for example, we're unable to identify a cow that appears on unusual backgrounds like sand, or we're unable to predict that an individual is healthy just because it's a female. So the challenge that we're going to tackle is how do we build invariances to a single shortcut? Of course, there can be multiple shortcuts in real life, but we're not trying to be exhaustive. And the key idea here is that we're going to approach this problem and look at it from the lens of causality. And we're going to try to pull ideas from causality to improve this prediction task. And we'll see that this approach takes us to a solution that looks similar to recently suggested work, where we end up minimizing something like the logistic loss while imposing an invariance penalty. But there will be key distinctions that are motivated by causal arguments. Let's look with a bit more detail at this cow classification example, which I'll use throughout as sort of a motivating example. Here we have images, and we want a predictor to tell us if the foreground object is a cow or a camel. At training time, we have the images and their labels. So the label Y is 1 if it's a cow and 0 if it's a camel. We'll also assume that we have the label of the background at training time, and we'll call that the auxiliary label V. So V is 1 if the background is grass and 0 if it's sand. At training time, the majority of camels are on sand backgrounds and the cows are mostly on grass backgrounds. And the other two categories have a non-zero probability, so we can observe some of them, but they are very underrepresented. And what we see is that at test time, we're unable to identify the cows that exist on sand. And we'll say here that the model has learned a shortcut. And what we mean by that is that the model uses the background as a shortcut to predict the foreground object at test time. So if you get a testing distribution that is different from the training distribution in that there are a lot of cows on sand and camels on grass, then your average accuracy deteriorates by a lot. And we've seen this scenario happening a lot recently. And before jumping into the meat of the talk, I wanted to sort of give you a roadmap that will guide the conversation. We'll start by defining the problem from a causal perspective. And then we'll look at asymptotic and finite sample guarantees that we can get because of our causal perspective. And this all will help us spell out a specific objective to optimize. And the last thing we'll do is we will look at the empirical performance of our approach. So what does it mean to look at the problem from a causal perspective? We'll start by defining the causal DAG, or directed acyclic graph, and I think most people here know that the DAG is a graph where the solid arrows encode causal relationships between variables. Shaded nodes on the graph mean that the variable is observed. White nodes are unobserved. We've already introduced x, y, and v. The new variable here is x star, and we see that the main label affects the image x through this x star. And you can sort of intuitively think about this x star as the spots of the cow or the mouth of the camel. The other thing we'll see here is that there's a dashed bidirectional arrow that shows that the two variables are correlated but not causally related. And what we want is a predictor that is invariant to any correlation between v and y. To define things a bit more formally, we have a source distribution PS, and we want a predictor F, which is the composition of a learned representation P and the final classification or classifier H. And we want this F to be accurate, and we want it to have the same performance across all members of this family of target distributions. Members of this family are the same as the source distribution, except that they have different correlations between V and Y. So the first advantage that we can get by looking at the problem through the causal lens is that this allows us to define a set of naturally occurring distribution shifts that we want to be robust against and sort of should be robust against. So what we've just seen is that looking at the prediction problem from the causal perspective allows us to define a set of distributions that we should be robust against. And next, we're going to look at this problem as defined through the causal lens. And now we're going to look at like the solution as defined through the causal lens as well. And the first thing that we are going to arrive at is an asymptotic argument. What we found is that there exists an ideal distribution where this correlation between v and y does not exist. So you'll see here that the bidirectional arrow between y and v is no longer in the DAG. And we'll call this distribution p circle. So intuitively, this is a distribution where you're equally likely to observe a cow on sand or grass. If our source distribution is this ideal distribution p circle, our estimator, what we found is that our estimator is robust asymptotically. And very briefly, this is sort of easy to prove because you'll notice that there's no backdoor between x and y, where that x star deseparates those two variables. And I think this crowd will also appreciate the fact that this distribution is sort of similar in spirit to the distribution of a randomized control trial because it has some nice independencies that lead to unbiased estimators. Okay, so we have a nice asymptotic property for robustness. We want to go ahead and look at the finite sample efficiency. Specifically, for the first couple of slides, we'll assume that we've sort of hit jackpot and that we've sampled from the ideal distribution where we're equally likely to observe a cow on grass or on sand. We should perhaps start by asking what kind of finite sample results do we want? What we really want to know is how does the risk on the observed data from some source distribution relate to the risk on any unseen target distribution? And we'll use R with a subscript PT to denote the unseen risk or unseen error on a distribution PT. And this is the probability of misclassifying an example. And we'll compare that to the error we are minimizing at training time, which we denote by R hat. And since we're assuming that we're sort of sampling the training data from the ideal distribution, we're going to index that R hat with P circle. And I'll refer to this difference as the generalization gap. Ideally, we want the difference between the two to be as small as possible. And that would mean that minimizing the training error also minimizes the risk that we care about. And of course, we can't empirically estimate this difference because we never observe the expected risk, which is the first term here. So even if just to really drive this home, even if the test data is sampled from the same distribution as the one that we observe at training time, we still would not be able to estimate this difference. So the best that we can do is to give some theoretical bound, and the smaller that difference is, or the smaller that we theorize that difference is, the better off we are. So if we say that this question mark is a small term, then we are in a better place. To analyze this generalization gap, we did this fun thing where we add and subtract by the same value. And here we added and subtracted the unseen risk on the same distribution as the training distribution. And this allows us to separate different components of the generalization gap that we can then analyze separately. The first component is the structural risk gap. And this tells us how much of our generalization gap is coming from the fact that we're training on one distribution, that is the circle, and then testing on another distribution, that is some PT from the family of distributions that we want to be robust against. The second component in this gap is due to the fact that we're learning from limited data. And this is sort of the usual generalization gap that you see in intro to statistical learning theory, and it will depend largely on the complexity of the function class we are considering. And we're going to go through those two terms, but in order to do that, we're going to need some way to measure distances between distributions. That will sort of prove to be useful in our theory. What we're going to use to measure these distances is the maximum mean discrepancy, or MMD. The MMD is just one way to do this. We use it because it made for elegant math, but it's likely the case that you can use things like Wasserstein distances and other things can probably be used here. The MMD measures how dissimilar two distributions are by measuring the distance between them in some embedding space omega. And we will take that embedding space to be the RKHS, or the reproducing kernel Hilbert space. we made that choice because it gave us some nice unbiased estimators and sort of nice non-parametric and flexible. So that was a good choice. What this math is telling us is that the way we compute the MMD is by picking the embedding function that maximizes the difference between the two distributions, and then you estimate the norm in that under that sort of embedding function. And specifically in this work, we'll be looking at how dissimilar are the distributions of the representations of images with sand backgrounds and images with grass backgrounds. And I will use this P with a subscript phi 0 to denote the representation, or rather the distribution over the representation for images with grass backgrounds. And similarly, we'll use P with a subscript phi 1 to denote the representations of the sand backgrounds. And we want those two distributions over the two representations to be similar. Intuitively, if they are dissimilar, then the representation encodes information about the shortcut, that is the background, so it's no good. So to give you a visual, the two plots on the bottom of the slide here show you the values of a one-dimensional representation on the x-axis, and the y-axis shows the two probability distributions that correspond to them. The plot on the left shows two distributions that are relatively similar to each other, so their MMD is small. The one on the right shows two distributions that are dissimilar, so their MMD is sort of large. That was sort of the end of a sidebar or a tangent where we defined measures on distributions. Let's go back to our problem. Remember that what we want is to bound the difference between the empirical error that we observe at training time on data sampled from the ideal distribution versus the unseen risk on an unknown target distribution. And we broke that down into two terms. We'll start by looking at the structural risk gap. And what we found is that the structural risk gap can be bounded by the value of the MMD. So when the MMD between the distribution of the representations of sand images and the distribution of the representation of grass images is less than some value tau, the difference between the risk on the target distribution and the risk on the ideal distribution is less than 2 tau. Remember that in order to get good models that generalize well, we want the structural risk gap to be small. So the smaller this tau, the better. And if you're sort of starting to think, oh, a good objective should minimize this MMD, you are thinking of the right thing. So that was the first term in our generalization gap. Let's look at the learning gap, which is the second component of the generalization gap. And remember that the learning gap is the part of the generalization gap that is due to the fact that we are learning from limited data. And what we found is that by imposing an MMD penalty in our learning objective, which implicitly encourages our model to encode independencies implied by the DAG, this leads to more efficient estimators without introducing bias. We'll look in a second at how exactly we sort of implement or enforce that penalty, but before getting there, what does this proposition really mean? Think of a simple example where we have two features. The first one affects the value of the auxiliary label v, and the other affects the value of the main label y. And again, to keep things simple, suppose we're only considering linear representations phi, and the final classifier is just a sigmoid transformation. Spoiler, this is basically a logistic regression. So we know that the optimal weights wv are 0. So the real function space that we want to consider is this one which allows wy to take on non-zero values, but it sets wv to be 0. So what happens if we decide to do L2 regularization? If we do that, our candidate function space becomes this yellow circle. And instead, what we're going to do, we're going to enforce this causally motivated regularization that penalizes the learned representations that encode information about V. And in doing so, we reduce the complexity of the function class that we're considering. So by imposing this independence penalty, or this causally motivated independence penalty, we can reduce the function space to something that, roughly speaking, looks like this blue oval. This penalty allows us to reduce the hypothesis space without introducing bias, which then translates into smaller learning gap. So this means that causally motivated regularization schemes give us not only robustness, but also finite sample efficiency. And I think this was sort of one of the big key takeaways, at least for me in this work, is that we not only are gaining robustness, but we are also gaining efficiency when we try to build models that conform to the causal DAG. So in the actual paper, we'll talk about this more formally, and we show that the upper bound on the Rademacher complexity of this causally motivated or causally regularized function space is smaller, and the smaller the tau is, the smaller our MMD is, the better off we are. So to quickly recap this part of the finite sample analysis, we found that when sampling from the ideal distribution, estimators that we learned there have a smaller MMD, or rather the ones that have a smaller MMD also have a smaller generalization gap. And remember that estimators that have a smaller MMD more closely conform with the causal DAG, since they don't encode spurious correlation. So this makes us conclude that estimators which conform to the causal DAG are more efficient. So this means that a reasonable strategy here would be to say, well, let's build models that force this or encourage this MMD to go to 0. The challenge that we run into is that none of this holds when the data is sampled from any distribution that is not the ideal distribution. So you can actually introduce bias to your estimator if you push the MMD to 0 when your data is sampled from non-ideal distributions. So we turned again to ideas from causality to address this issue. In causality, we see this a lot. We have a notion of an ideal distribution, which is the distribution of a randomized control trial. And we often reweight the data to mimic the independencies that exist in a randomized control trial. And we did something similar here, where we used weighting to map us onto a distribution that looks like the ideal distribution. And this helps us recover the independencies from the ideal data. So it's great. But the caveat here is that weighting leads to higher variance estimators. So we're not exactly at the same place as we would have if we had sampled from the ideal data, but we're sort of like close enough. All right, so let's look at how all these insights translate into an objective to optimize. So our objective will be to minimize the weighted logistic loss and a penalty term. Alpha here is a hyperparameter that we're going to pick during cross-validation. And this penalty term is an estimate of the MMD. So if the MMD is 0, that means that there's no information encoded about V or the shortcut in the representation, and that is a good thing. So the lower the MMD, the better off we are. And when we define the MMD to be the sort of family of bounded functions on RKHS, we get this nice estimator where K is the radial basis function. So this is really computing the norm in RKHS, or rather, to be more explicit, it is the weighted norm in RKHS. So it's important to note that both this MMD and the logistic loss are weighted by U, which is the set of weights that we use to sort of like map us onto the ideal distribution. Otherwise, we might end up with a biased estimator that is sort of overly conservative in the way that it imposes these invariance penalty. Great, so how does this all perform in practice? We wanted a data set where we can control the correlation between Y and B, both at training and at test time. So instead of using sort of naturally occurring images, we simulated a data where we looked at images of land or water birds and superimposed them on land or water backgrounds, as you see in the slides. So it's really semi-simulated data. Our task here is to predict whether the bird in the picture is a land or water bird. So the main label Y is the type of bird, and the auxiliary label V is the type of background. It's either land or water. And we're going to fix the training or source distribution and look at the performance across many test distributions. Looking at the results, we have on the x-axis is the correlation between the background label and the main label at test time. And this dashed line shows where the training distribution is, or like this conditional probability during training time. The y-axis will look at the AURC at test time. Both our suggested approach and all the benchmarks that I'm going to present are all ResNets, and we will compare our model to an L2 regularized model. So this is simply a ResNet where you add weight decay. And we also will look at WL2 is a weighted L2 regularized model which it uses the same weights that we use, but it doesn't have the MMD penalty. And the final model is a model that does random augmentations. So it augments the data at training time by introducing transformations such as random crops, rotation, brightness, sort of augment the data at training time. And what we see is that our approach has a better AUR/C at every target or every test distribution. I've also added results from a model that enforces this MMD constraint or the invariance constraint without doing the weighting scheme that we did. And what this model is sort of doing is that it's blindly applying the MMD constraint, and what it does is it ends up being overly conservative. It loses information that we need to make good predictions. But the general takeaway from the slide is that building models that are consistent with causal structure leads to robustness to distribution shifts. But this next part is the part that was somewhat surprising to me when I sort of like went through this project, though it is confirmed by the theory that I just presented. We redid this experiment and we looked at data that was sampled from the ideal distribution. So you see this dashed line where the training data is sampled from, meaning at training time, you're equally likely to observe a water bird on a water background or a land background. And what was surprising here is that even when there's no biased sampling at training time, we do better by enforcing these causally motivated regularization schemes. And sort of even if there's no distribution shift, we get more efficient models that do better within distribution. So yeah, so this is to say, like, even if you don't think that there will be a distribution shift in your setting, you're better off doing this causally motivated regularization than healthy regularization. And you can see that by looking here. At this point, the training data and the testing data come from the same distribution, but still we do better than the normal regularization or augmentation methods. Really quick, I'll show some results on a less contrived data set. Here we use a data set of chest x-rays, and we downsampled the females who have pneumonia at training time. And the task here is to predict the onset of pneumonia, which is our main label. And we want to make sure that sex is not a shortcut. And again, we see that our approach has a better AUR/C when there is a distribution shift, which is sort of the first row on that table you see. And even within distribution, we do roughly as well as the best. So to sum things up, what I showed you is that causally motivated regularization schemes lead to robustness against distribution shift. And even when there is no correlation in the data or no distribution shifts, enforcing these regularization schemes that are consistent with the causal DAG can lead to more efficient estimators. And that's my favorite part of this work, at least. But these causally motivated regularization schemes have to be implemented with some knowledge of the underlying DAG and the spurious correlations in the sample data. Otherwise, you might end up with overly conservative and biased estimators. So if you're interested to dig into this more, the work is up on arXiv, and I am going to stop now for questions. There you go.
So we don't currently have any questions. Maybe we can wait a few seconds to see if any come in.
That means I was either very confusing or very clear, one or the other.
So feel free to submit your questions if you have any.
I think probably someone can also raise their hand. There's a question.
There is a question. So the question reads, besides the background, are there other examples of spurious correlations that you have encountered?
Yeah, I think the chest X-rays example is one where there's no like background shift. It is like you tend to like if you see a female, then you are more likely to sort of predict that it's pneumonia or it's not pneumonia, just based on the shortcut that is the sex of the patient, as opposed to like actual disease. But there's also like
actually.
Go ahead.
Oh, sorry. Yeah, I mean, that particular example, I think, is highly relevant given some discussion that's been going on recently about what patient characteristics can actually be read off of something like an X-ray. Right, so there's currently some work also saying that a patient's self-reported race is something that you could recover with quite high fidelity from these kinds of images, right? And again, I think that there are concerns about the potential for machine learning models to learn shortcuts.
Great, thank you. Oh, we got another question or a couple questions coming in. So this one, and as Emma said, you should feel free to also raise your hand and then maybe we can unmute you. Okay, the first question reads, does this idea of removing an arrow to avoid shortcuts have any relationship to the fairness work done by Nabi, Spitzer, others who also talk about eliminating an arrow to recover a fair world?
Yes, this work has a lot of relevance to fairness work in general, because fairness work also tends to fall in the sort of kind of work where you have an invariance penalty. I would say that the objectives of the two kinds of work are very, you end up with a similar looking solution, but the way to get there and the objective of the study is very different. In that, for example, in fairness work, you typically want to make sure that the invariance penalty or the invariance property is satisfied to the best of your ability. Whereas our objective here was to make sure that we have good accuracy and good generalization. So sort of the theoretical approach of these two kinds of work is dissimilar. The other thing is, because this objective or the final goal is not that similar, you don't need to do the reweighting scheme, or you might not need to do the reweighting scheme if all you need is to make sure that this invariance penalty is satisfied. But if your end goal is to generalize beyond this observed distribution, you will have to do this weighting scheme. Alex and I have been talking about this a lot recently, so I don't know if you want to add to that.
I just think one other interesting thing is that like a point that's made in Razieh and Ilya's work there is that there's a lot of judgment that goes into deciding which pathways you think are relevant or not, and deciding what's fair or not. And I think quite similarly here, there's a lot of judgment that has to go into which kinds of pathways for correlation or for dependence you would like to remove or you'd like to preserve in the problem.
Okay, maybe we can just do one more quick question. So the question is, what if we used KL divergence or symmetrized KL instead of MMD? Would that be worse?
That's a great question. I have not played with the KL divergence. I suspect that you can add different measures over distributions, and you may even end up with like slightly different guarantees, like finite sample guarantees. That would be very interesting to look at. I have not played with that myself, but yeah, theoretically, other measures over distances are plausible.
Okay, great. Thanks so much for the great talk. I think